Let us look at the Fourier transform of phi t in the Haar context. Essentially, it is this, and the Fourier transform is easy to calculate. Now, we can simplify this. Using the standard trick of taking out e raised to the power minus j omega by 2 term. And then we note that we have a sign hidden there. And doing away with the j's, we will have Now, as you can see, this Fourier transform goes towards 0 as capital omega goes towards infinity. So, the Fourier transform vanishes as capital omega goes towards infinity. And in fact, we can even sketch the magnitude to get a feel of this. The magnitude of phi cap omega looks like this. You see, at omega equal to 0, you will notice that one can use L'Hopital's rule and show that this is equal to 1 in magnitude. So, it has a pattern like this. Of course, we know where this comes. This will come at omega by 2 equal to pi or at 2 pi. This would come at 4 pi and so on. This is how the magnitude looks. Now, you know, this very clearly shows that phi has a concentration around 0 frequency. So, this is interesting. We begin from the low pass filter, we construct a dilation equation, a recursive dilation equation starting with a low pass filter, and we get a low pass function. Phi t is essentially a low pass function. A low pass function means it is predominant in the frequency domain around capital omega equal to 0. Low pass function, of course, is an informal term. You may always argue that after all it does have bands at higher frequencies too, but the point is its prominent bands are around 0, and the farther you go away from 0, the more the spectral magnitude drops off. In that sense, it is low pass. In fact, just as we tried to build the idea of ideality in a filter bank, we also would like to build the idea of ideality in this phi t. the ideal phi t is actually the ideal low pass function. It is a low pass function which is like a brick wall. So, in some sense phi t in the spectral domain or phi cap omega for that matter is moving towards the ideal this is where we are moving. And where we are is somewhere here. Very far away from it, of course. Not surprising, after all, that is what we saw in the Haar multi-resolution analysis too. Ideal here, actual there. Now, once again, there is the same conflict that drives the engineer, the scientist or the mathematician. We know that we want to go towards the brick wall ideal, but we also know the brick wall ideal is unattainable for various reasons. The reasons are similar to what I talked about last time for the unattainability of the idealism in a filter bank. So, we would not need to repeat them once again here. However, what we will now do is to see what is the relationship, whether ideal or practical, what is the relationship between phi cap omega and the discrete time Fourier transform of the filter bank, low pass filter, in terms of construction. So, in other words, we have written down a dilation equation in the frequency domain, but we need to translate that dilation equation into a constructive step. How do we construct phi t given the low pass filter impulse response? In a way, if we do that, we have answered the question, how is the design of a filter bank related to the design of a multi-resolution analysis? So, let us do that. Towards that objective, let me put before you once again that infinite product here. So, now you also understand why phi cap 0 should not be 0. Phi cap 0 must be non-zero. In fact, phi cap 0 is very often the maximum value of the magnitude of phi cap omega, because of that low pass character. So, we have seen this low pass character in the Haar context. Now, we shall assume it to be true of most multi-resolution analysis and proceed from there. So, this is just a constant, a non-zero constant, to be wary. But what we need to identify is this.